please, if you're not asking a question or participating, but by all means participate. So keep your camera on, mic muted, but don't hesitate to ask questions. And please pay active attention. Don't be driving. You know, don't be sleeping. Don't be horizontal in your bed. You know, all right. Here we go. Hope everyone had a good weekend, despite a little bit of snow now. I hope the weekend was good for everybody. We're going to get dumped on here from what I hear. From what I hear, this is going to be upwards of a foot, which of course is nothing for compared to eastern Montana, right? You know, we're going to get started here. Where are we at here? Right here. I think we left off here last time. I remember covering this slide. This was just the advantages, pros and cons, properties of each type of measure of center. Some exhibit high sensitivity to outliers, some not. If the distribution, if the data are distributed more or less symmetrically, then there's not much difference in any of these. But if they're not symmetric, the mean and median make a good pair. Skewness, in the middle you see something that's symmetric, and that can take various forms. It doesn't have to be a mound shape like that. That can take various forms. I want to see something here. Do we? No. Just a minute here. I'm going to stop for a second and get my ink going. What's that? Smart ink. Let's get that going. Let's see if that works. No, still not working. Smart ink is not working. Smart ink. Why is Smart ink not working? It doesn't like me this morning. We're going to do talk about skewness here a second. If something is symmetric, the data have like a center axis to them, right? And if you reflect the distribution around that center axis, it's a mirror of itself. I need to get, there we go, good. Finally got my markers working here. I want you to notice the order, say on here on the left, if you have something that is skewed right, that means that the tail, the thinner tail of the data is on the right, okay? And the clump of the data is on the left. Now, the thinner tail is where the outliers are going to be. And the outliers pull up the mean the most because the mean is more sensitive to outliers. The median, not so much. And the mode is always at the very top of the distribution. Now here, of course, in the middle, mean, median, and mode are all the same. Right. And on the right-hand side, you have something that's skewed left, and that means the tail is in points left. And that means the mean will be the leftmost of the three because it's being pulled left by the outliers in the left tail. So basically, the direction of skewness is the direction of the tail, right? If the tail is right, it's skewed right, left, skewed left. Here's an interesting it's a paradox, really, but watch. Suppose that I think my wife doesn't spend her money wisely. Let's suppose that's true. All right. She disagrees. So we make a deal that whoever spends less on average when we go shopping next week has to make the other's favorite dish for dinner. Okay? My wife reminds me it's been ages since she's had filet de sole. Okay. So we're going to go shopping. We go to a shoe store, and naturally my wife goes bonkers, right? 7 pairs of shoes. Okay. 7 pairs of shoes. Spends $280, which is $40 per pair of shoes. Okay. Me, since I spend my money wisely, right? I buy 2 pairs of shoes, but they're $60 a piece. Oh no, $60 total. I'm sorry. So $30 a pair. So she spends $40 a pair. I spend $30 a pair on mine. I average $10 less per pair, and I can smell an Angus steak coming in my general direction. Okay? So that's the shoe store. Then we go to a clothing store. I buy 6 items at the clothing store, spend $420, $70 per item. My wife buys only 3 items, $240, but that's $80 per item. Okay? So I spend $70 per item. She spends $80 per item. And I, once again, average $10 less. And I would like that Angus steak medium rare, please. Now let's combine our shopping efforts. My wife quickly points out that she bought 10 items for $520. 10 items, $520, $52 each. I bought 8 items for $480, $60 each. Now, I averaged $10 less at the shoe store and $10 less at the clothing store per item. And yet, when you combine them, my wife's 10 items were $52 a piece. My 8 items were $60 a piece. So she spent an average of $8 of less per item when we combine our shopping. So should I head to the fish market, or is it surf and turf? Does anybody have any ideas how this would happen? How can I average $10 less at the shoe store on average, $10 less at the clothing store on average, and she wind up $8 less on average when we combine the two? How is that possible? Anybody have any ideas?
Well, she bought a lot more items than you did. So her total value will be divided by more, but like it still doesn't make a lot of sense to me.
You're on the right. You're in the right direction, right? It's got to do with the fact that she bought more items at the cheaper store, which was the shoe store, right? She bought more items at the cheaper store. All right. I bought more items at the clothing store, which was $70 an item, $80 an item. So I bought more items at the more expensive store. She bought fewer there. And so even though mine averaged less, I spent a lot more at the more expensive store. So go back over here. All right. So this is called Simpson's paradox. It has been around a long time, and it can lead to some really crazy results sometimes. It's when the relationship between two variables reverses when a third variable is introduced or is controlled for. So when we take into account a third variable, the result reverses. What was the third variable? The third variable that got controlled here was the store we were shopping at. You know, if the shoe store was Payless Shoes, and the clothing store was, say, Dillard's, right? I bought more items at the more expensive store. That's lesson number one. When you control for which store we're shopping at, my apparent advantage of spending less per item went away. It reversed, in fact. Number one. Number two, you really shouldn't average averages, right? You can't really average averages. And by that I mean my average at one store and the average at the other store were both less. But when we try, you would think that when we added them together, I would be $10 less per item. And that wasn't true. So this can lead to some really weird research results. Let me give you another example that I'll just tell you off the top of my head. I have the example written out, but I don't have it in the slides. I made up the example, so I'm pretty proud of that, right? It's possible, you're not going to believe this. Suppose two students go to, say, York College. Two students go to York College for 4 years, 8 semesters. Okay? And they go the same semesters, right? They go exactly the same semesters. If one goes a summer, the other one goes a summer, take something online, what have you. It's possible for one student's GPA to be better every single semester, and yet the other student have a higher GPA. That doesn't seem possible, but it's true. It is possible for one student's GPA to be higher than the other one's every single semester for 4 years, and the other student have a higher GPA. And what you're not controlling for here is the number of classes you take per semester, the number of credit hours. All right? So let's suppose that during the summers when you only take one class, let's suppose the one student got like an A every summer and the other one got a B. They took one class over the summer. Okay, so the one student gets an A, the other one gets a B. Now let's suppose when the school is in session, the one student makes, say, a 2.5 GPA, the student who got the A over the summer, and the other one gets like a 2.3 GPA, 2.5, 2.3. Under a situation like that, I'm thinking out loud, I haven't done the calculations. Under a situation like that, the student, especially if the student doesn't take as many classes. For example, if the student who got the A over the summer only takes, say, 4 classes during the school year, another one takes 6. And then over the summer, the one who gets a B over the summer takes or averages a B. Maybe they take 3 classes over the summer, and the other one only takes 1. So if you play around with how many classes they take each semester, you can get one student, and I have an example worked out like this. One student makes a higher GPA every semester, but because their course loads are different, the other student winds up with a higher GPA. So anyway, that's Simpson's paradox. Keep that in mind and be suspect every time you see averages being averaged. Don't do it. Don't do it. This can lead to some aberrant research results. All right. The punchline: you can't average averages. Oh yeah. You know what? I don't know if I gave you any more slides. Uh-oh. Shucks. Well, I have them here in the classroom. Okay. Well, we're going to have to go. Unfortunately, we're going to have to keep going on. We talked about measures of, there's going to be 3 descriptive statistics, types of descriptive statistics we're going to be covering. One is, you know what, there's a lot of noise outside. I'm going to go and shut a couple windows. We're going to be covering 3 kinds of descriptive statistics. You remember at the beginning. One of them was measures of center. This one here is measures of variation or measures of spread. The third one is measures of relative standing. Where does a data point stand? Where does it rank in its data set? All right. So measures of variation are our next one. And these behave a little bit different than measures of central tendency, measures of center. All right. Remember we had 4 measures of center: mean, median, mode, mid-range. Well, we're going to have a few different kinds here. One is the range, and we've already used the range. We used the range when we did a frequency distribution. You remember we took the highest one minus the lowest one? That's the range. And we divided by the number of frequency classes we wanted. That's the range. So the highest minus the lowest. Then there is the variance. Variance. Notice for a population, you have the Greek letter, lowercase sigma. For a sample, you have a lowercase s. So once again, the Greek letter goes with the population, right? And this is kind of a strange calculation, right? The variance. What you're doing is you're taking every data point. We're going to be doing this here in a second. You take every data point and you subtract the mean from every data point. So those data points that are above the mean, that when you subtract the mean, that will be a positive number, right? And by the way, x minus mu is called a deviation, right? Now, deviation is just simply a data point's distance from its mean. But this can be plus or minus. Right? Obviously, if it's above or below the mean, that will be positive or negative. However, if we did that, the more spread out data are, you'd expect them to have more deviations, higher deviation. But if we did it this way, just did x minus mu, the positive deviations, if we added them up, would cancel out the negative deviations. And you don't want that to happen. And so what we do is we square them. We square them. And here is a big difference. I mentioned that, I told you this was coming. For the population variance, you divide by capital N. You divide by capital N, and capital N is the population size. For a sample, you divide by, this is the big one, the sample size minus 1. Not in, but n minus 1. So that's a little bit different. The formula is a little bit different for sample variance than it is for population variance. All right. It mentions down here it's a deviation. I think I didn't need to write that above. Now, when you take the square root, we actually don't use variances a lot. And the reason why we don't use variances a lot is that in your units of data, suppose you were doing the average age of a class, or you were taking, the ages of people on the, basketball team. The variance will have squared units. So it will have units like squared years. Instead of 21.2 years, it's going to be 21.2 years squared. So those are weird units. More often we use what's called the standard deviation, and the standard deviation is just the square root of the variance. The square root of the variance. Now, something I want you to keep in mind, because I am such a swell guy, right? Y'all know that, right? I am going to give you formulas on the test or any quizzes we have. So your formula card right here, if you can see the camera, this formula card that comes with the book, I'm going to be handing one of those out with your tests. Okay? Except for one page. And there's one page of this that is not formula. It is actually content. There's one page here. And it's the very last page. It looks like that. You won't get this page here, but you don't care. You won't care about this until down the road. Okay. But all the formulas on one side, you're going to have probability distribution tables. On the other side, a million different formulas. You'll have that on the test, except for that one page. So these two formulas you're going to have, but you need to know how to use them. And of course, you need to know how to find them on your calculator, right? So let's do the standard deviation for our class ages here, right? There's it all worked out, but I'm going to show you how this works. So for every data point, you're going to compute the deviation. Now, remember the mean here is 19.5. So if you take 19 minus 19.5, that equals negative 0.5. And if you square it, you get 0.25. So what we're doing is we're applying this formula. Let me see here. We're treating this as a population. All right. So we're applying this formula here on the left, which means we have to compute the sum. This sigma means the sum of. The sum of the x minus mu squareds. Here's what I mean. Here's the x minus mu minus 0.5 squared it. That gives you 0.25. 21 minus 19.5. That is what? 1.5 squared is 2.25.
Mr. Miller?
Yeah?
So is our mu value just the average?
Yeah, it's the mean. Yep.
Okay, thank you.
And in this case, we're treating it as a population. So it's mu. Well, that's why I have mu there, right? The calculation wouldn't be any different for the mean if it were a sample. So that's where the 19.5 comes from, right? And so you have 18 minus 19.5 is minus 1.5. Squared is another 2.25. The next one's an 18. That's going to be another 2.25. For that matter, any other 18s are 2.25. These 19s right here are going to be 0.25. 0.25, those two 19s, right? 22 is going to be a little tricky, but 22 minus 19.5 is 2.5. Squared is going to be 6.25. 20 minus 19.5 is 0.5. Squared is 0.25. And that goes for this one down here. And that goes for this one here. That 21 gets a 2.25. And then I have a 17. 17 minus 19.5 is negative 2.5. Squared is 6.25. And so what you get is what's on the next slide. Okay? This is that chart completed. Now, for our formula, we need to sum this column. And that gives me 23. That's called the sum of squares. The sum of squares. And the 23, you see, goes right here in my formula. Since it's a population, I divide by 12. If it were a sample, I would divide by 11. But since I'm doing the whole class, I'm treating the class as a population in this case. You've got to know from the context of the problem whether it's a population or a sample. Okay. By the way, anything involving surveys is a sample. Right? All right. And so my population standard deviation is 1.38. 1.38 is what that comes to. Now, if we include the age of the instructor, you remember him? It goes from 1.38 to almost 12. Yeah. Now, that makes sense in one way. Doesn't it make sense that a measure of spread, a measure of variation would be sensitive to outliers? So all measures of variation are sensitive to outliers. And we saw before, only some measures of center are sensitive to outliers. So in this case, if we throw his age back in 64, the standard deviation explodes from 1.38, about 1.4 to 12. Now let's do this on the calculator, right? Let's see here. Go here. My calculator. Calculatus, eliminatus. Okay. Okay. Now, we had some data in here before. Let's look at stat, edit, and you remember we had these we entered it as a frequency distribution. I'm going to go over here. I'm going to go up, clear down, up. My calculator froze. It seems like when I first bring out my calculator, it freezes right away. And then it works okay. Let's try it again. All right, stat. Oops. Enter. Back over here. Go up. Oh, okay. Oh, now it's writing on the screen, which means I have to find a way to shut off my smart ink. me shut it off. You gotta shut it off before you can calculate here. Well, you know what we're gonna do? Do it the hard way. Smarty, bye-bye. Right. Now, let's try this for the third time. Go up to the top, hit clear down. Up to the top, clear down. All right. So L3 and L4. Let me see here. Rid of that. I need to get these data here. I wonder if they'll let me copy those in. Would be interesting. Let me copy those in. I don't know how to paste. All right. I'm going to figure out a way to put those on the screen. Well, we'll do it the really hard way. 19, enter. 21, enter. 18, 18, 22, 18, 18, 22. 20, 17, 19, 19. 20, 17, 19, 19. Last 20, 21, 20. 20, 21, 20. Okay. All right. So now I have the data in L3. So I'm going to click out here. And I'm going to go once again to stat, calc, one variable stats, and I want my list instead of L1. I'm going to go second, L2. I don't want to use this frequency list that I used last time. I'm going to put just a 1 there. Go down to calculate. What's going on? Maybe I just have to clear that. Clear that. Calculate. That is, of course, incorrect. That is way incorrect. Let's go back to my list, stat, edit. Here's L3 right here. L3, second quit. Stat. No. Where are the stats? Oh, I did L2. I need L3. That's the problem. Enter. Okay. So here we have the 19.5 we had before. A lot of this data looks the same, right? Here's the 19.5 we had for our mean. 234 was our sum. Here's the 1.38. And I want you to pay very, very careful attention, grasshopper. Okay? Look, sigma is the population standard deviation. That's what we just calculated. It's 1.38. What is this one here, SX? That is the sample standard deviation. Why does it give me 2? Because the calculator doesn't know if those 12 data values are from a sample or from a population. It doesn't know, but you know, right? So if you were to use the formula for and treat it as a sample, you would divide by n minus 1 instead of n. and dividing by n minus 1, which is smaller, you will get a slightly bigger number, 1.45. Slightly bigger than 1.38, right? And this is actually the same screen we got before, all right? The same screen we got before. Now, if you wanted to treat this as a frequency distribution, like we did before, you go stat, calc, enter, one variable stats, and instead of L3, we're going to do L1 and L2 again. We can do second, L1, second, L2, calculate, and you get the exact same values, which you should, because they're the same data, just rearranged into a frequency distribution. All right? All right, now I mentioned before, if you go down to the second screen, you go down a little bit, you're getting these n equals 12. You see minimum, 17, maximum was 22, median was 19.5. We're going to get into Q1 and Q3 here in a minute. All right, any questions? So that basically describes that screen. Now, I said if you did it as a frequency distribution, you would be using different formulas. These are the formulas for standard deviation using a frequency distribution, and they got that little f in there. See the little f? That's the frequency for that particular data point. And you would have that in a frequency distribution. And naturally, you get the same results, right? If we did this by hand, which we're not going to crank through, but there's actually less calculations here. Because you calculate every deviation, you calculate every deviation only once. Here, I want to mark on the screen. You calculate every deviation only once. All right? All right, that describes how to do that. This is a summary sheet for the formulas for standard deviation and, of course, variance, right? Variance would be squared. You're going to use standard deviation more. For one reason is that it represents the sort of like almost the average distance that a data value is from the mean. The second reason is you're going to use standard deviation more is that you don't have it has the same units as the data. You don't wind up with square years or square pounds, etc. Okay? You wind up with the units the same as the data. So they're easier to interpret. So that's a summary there of the formulas for the population standard deviation and sample standard deviation. And keep in mind, these are the same across the board. Oh, one little detail I haven't talked about yet. These sum of squares, there's a shortcut for the sum of squares. And that in the circle equals this stuff. Now that doesn't look like a shortcut, but it is. It is, because you don't have to compute deviations. Here, you have the sum. Here you have the sum of the x squared. So you square them first and then sum them. Here, you sum them first, then square them and divide by n. So that is a sum of squares shortcut. For small data sets, it doesn't matter much. For larger data sets, that's a huge savings. All right. So using the shortcut, let's use this shortcut here on the right to compute the same standard deviation that we did before. So here we have our x squareds. Take your x values, this column here, and you square it. That is 289. 18 squared, I believe, is 364. Is that it? 324. 324. 324. 19 squared, I got them on the next one, 361. 20 squared is 400. 21 squared is 441. And 22 squared, 484. Now, the next column, I take my F value and multiply it by X. So my F times my X is 17. My F times my X, 2 times 18, 36. 3 times 19, 57. 3 times 20, 60. 2 times 21, 42. 1 times 22, 22. And you've got to sum these, okay? And the last ones, you take this, for the last column, you take this column and multiply by your frequencies. The numbers get big, so I'm just going to click here. These numbers get big here. So once you complete that column, you are interested in down here. These are the sums. And so here's our formula up here. The N is 12. The sum of the F times X squareds is 4586. Right? The sum of the frequency times the X's squared, that's this column, 234 squared, all divided by 12 squared. It comes out to the square root of 276 over 144, which unsurprisingly is still 1.38. My only purpose in doing this slide is this exercise is to use the shortcut formula. You may like it better or not. It's
Where
okay.
did the 12 squared come from again?
That's the sample size, or excuse me, the population size.
Okay.
That's the capital N. Good question. If there's something that needs to be clarified, any of you, please speak up. All right. This here is fun. This is fun. The empirical rule. It's a sort of a back of the envelope rule of thumb calculation that to me is interesting. Okay. When you have bell-shaped symmetric distributions, they have some special properties. Their mean, median, and mode is going to be in the middle, right? And if you go out one standard deviation each way, you go one standard deviation that way, one standard deviation that way, you will trap about 68% of the data between those two values. 68% of the data in between those two values. Right? So around in a symmetric mound-shaped distribution, around 68% of the data lie within one standard deviation of the mean. If you go out 2 standard deviations, 95% of the data lie within 2 standard deviations of the mean under the assumption that the data are symmetric mound-shaped, bell curve-ish, okay? It's called the empirical rule. Within 3 standard deviations, you have almost all of the data, almost. 99.7% of the data lie within 3 standard deviations of the mean. You got a little bit out here and a little bit out here. Okay? All right? So now you can break that up. You can use those to break up. Under the curve lie 100% of the data, right? 100% of the data are under the curve somewhere. And so you can see between here and here, you have the 68%, between there and there. You see that between here and here, you have 95% if you add those up. But now, what's the difference between 68 and 95? 27%. So 27%, we put half of 27 there, 13 and a half, half there, 13 and a half. And then from 95% to 99.7%, that's 4.7%. So half of 4.7% goes here, 2.35 goes in this tail, and that ends at the third standard deviation, right? And then there's 15/100% lie beyond 3 standard deviations. So that's 15 data out of 1,000. 15 data out of 1,000 lie beyond the third standard deviation on the top side, and the same on the bottom side, right here. Okay? And you notice from here to here, that's 99.7%. Okay? 99.7%. All right, so this is a breakdown of the empirical rule. And we can use it. Let's use the empirical rule. Okay? Assume that the average graduate from Podunk College. Now, I used to use your college. But you know what it is? What happened is that people started to use the real information they knew about your college and say, oh, that example's not right. And so instead of updating all my examples all the time for the current, whatever's current at your college, I just went to Podunk College. Okay. So assume that the average graduate, that's a graduate of Podunk College, takes 4.6 years of full-time school to earn his or her bachelor's degree. 4.6 then is mu, right? With a standard deviation of 0.6, that is sigma. If the underlying distribution is bell-shaped, we got to have our assumption. That's our assumption. Approximately what percentage of Podunk College graduates earn their bachelor's degree in under 3.4 years? Under. Okay. Let's make a little drawing. So we make a little drawing. This is 4.6. If I go up 0.6, I get 5.2. That's one standard deviation. I go up another one, that's or whatever, 5.8. If I go down one, I'm at 4. I go down another one, I'm at 3.4. So they want to know what percentage earn their bachelor's degree in under 3.4 years. So they want to know how much area is under the curve right here, right? How much area is there? Well, if you go back to this slide, in those two quadrants, or those two areas, there's 2.35 between 2 standard deviations and 3 standard deviations. There's 0.15 after. So I want those two added together. There's 2.35 here and 0.15 here. So 0.15% plus 2.35% is 2.5%. That's the percentage who earn their bachelor's degree at Podunk College in under 3.4 years. By the way, there's been some people do their bachelor's degree here in 3 years at your college. As I recall, Dr. Shannon Leinen was one of them, who is now like the head of our online. She was a student when I got here. B, approximately what percentage of Podunk College graduates take between 4 and 6.4 years to earn their degree? So let's make a little chart. 4 and 6.4. So this is 4.6. All right, 4 is down here. 1 standard deviation down, right? 6.4. Well, if I go up 1, that's 5.2. Another one is 5.8. Another one is 6.4. So I want to know what percent is in this area right here, not including this tail out here on the right and not including the tail on the left. Well, I can add things up. There's 34 here, right? 34 here. There's 13.5 here. And there's 2.35 here. So I add up 34 plus 34 plus 13.5 plus 2.35. These two add to 68. These two add to what? 15.85. And yeah, those two together is 83.85%. Okay? We're all out of time. Gonna let you go, leave it there. We'll pick up on this slide next time. All right?
Thank you, Mr. Miller.
See ya.
Did you see the email that there's no Ignite tonight?
I know. I'm so sorry. We finally got one. You know,
I know.
I don't think many would come. But
Yeah.
yeah.
Okay.
Thank
I
you
was
for the
gonna
reminder.
come, okay.
What's that?
I said I was gonna come,
Okay. Well,
but next Monday I got you since it's canceled today.
yeah. But the thing is, please come see me in office hours though too.
Oh yeah, for sure.
I mean, you can. I mean, I would love to see it.
Okay.
All right.
Sounds
Thank
good.
you.
Be
Bye-bye.
careful on the road.
Yeah. Oh, thank you. You too.
All right. Bye.